Let's look at example 1 to review what we've learned about our reflections here. So given the graph of y equals f of x, that's this graph right here. We're going to graph y equals negative f of x. So I've labeled the first grid paper for that. And then we'll label the second one down here when we get to y equals f negative x. So y equals negative f of x means the negative is going to be in front of the y values. So it's going to be x times negative y, which would cause a reflection over the x-axis. Now, if you need to, you can list out these ordered pairs, but I find that a little bit time consuming. I'm usually able to kind of just picture if this was now at negative 3, it's now still at negative 4, but now at positive 3. So if this was 3 below at the negative 4, it's 3 above. So I'm going to go, this has got my scale in it, 1, 2, 3, 4. So instead of being at negative 3, it's now at positive 3. Same thing would be with B, which would mean it's 2 over, all right? If it's reflection on the x-axis, this C value doesn't move, so that would still be at 1. And then D, instead of being at 3 positive 4, it's going to be now at 3 negative 4. So down at negative 4. And D is at 5 negative 4. Now it's going to be positive at 5 and positive 4. So I'm going to go 1, 2, 3, 4, 5, and now up at positive 4. And we're going to connect that. So it's still the same shape, it's just reflected. I'll use a pen so you can see that a little better. Now, one of the things you noticed is that the x-intercept, because it was reflected on the x-axis, did not actually move. We call that an invariant point. An invariant point is a point that stays the same after transformation has been applied. So in this particular case, this would be an example of an invariant point. It was the same on the f of x graph as it is on the transformed graph. Now let's look at the second one here, y is equal to f of negative x. This is going to reflect the y-axis now, which means that you would have negative in front of the x, which is clearly shown there. Nothing happens to the y value. So I'm going to take this a value, and instead of being at negative 4 on the x-axis and negative 3, it's going to be flipped over this way. So I'm going to go 1, 2, 3. So negative 4 is now positive 4. It's still down 3. Same is true from B, or I know if this is flipping over this way, it's 2 from that point. All right. Then my C, instead of being at negative 1 on the x-axis, is now on, or sorry, positive 1 rather, is now on negative 1, I meant to say. So there we go. Then my D value here is at positive 3, positive 4. So now it's going to be at negative 3, positive 4. And then my final one here, E, is at 5, negative 4. Now it's going to be at negative 5, negative 4. So 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, so let's connect those points. I'm still using a pencil. Hopefully that's dark enough. Yeah, it's dark enough for you to see. So this is the reflection in the y-axis where we've changed the negative signs. Again, looking at invariant points, there is an invariant point. Maybe it doesn't stand out as much on this one because it wasn't one of the A, B, C, D, or E values. But if you would notice that the y-intercept was negative 1 here, and on this one, we didn't plot that point, but it clearly goes through negative 1. And it would make sense that if you're reflecting over the y-axis, the point on the y-axis itself doesn't change, just like here. So in this case, the invariant point would be the y-intercept. So there is also an invariant point right here. You don't always have to label these, only if you're asked for them, but I want us to make sure when you're asked for invariant points, you'd be able to locate them.